Go live. There it is. And we're back. Excellent. For those of you that are online with me now, I see there are multiple people. For those of you that are in the classroom, did y'all hear about Pinelands? I had a letter forwarded to me yesterday that was addressed from the superintendent of Pinelands schools, where they received some concerns from the teachers union in the Pinelands Regional District. And they basically were like, okay, we hear you. For the first week in January, we're going to go fully virtual. And then at the end of that week, we'll reevaluate and determine whether or not we need to continue going virtual. And I'm like, wow, that was easy. So Pinelands is virtual this week. Stafford is virtual indefinitely. It's like, and here we are. Anyway, we'll see what happens. Anyway, counting today. You have 7 class periods until midterms. I repeat that. You have 7 class periods until midterms. I have you 3 days this week. I have you 2 days next week. The third week in January, you have that Monday off for Martin Luther King Day. So I also have you 2 days that week. And then beginning Monday the 25th are midterms. Oh, yes. Midterms are ready and raring to go. We're going to be, of course, reviewing the closer we get to the end of it. But there are still some things that obviously I need to teach you in regards to this new chapter that we've been covering. So what I would like to do is kind of twofold. Number one, I want to introduce to you the next concept that I'm going to be covering. But I'm going to show you at some point how it relates to what we were doing before break. So if you do not already have them out, I'm going to need those notebooks out and open. Ooh. All right. Flip that over. There we go. Boom. Anybody an Eagles fan? Eagles fan?
No.
All
I
right.
hate them right now.
Giants fan?
Yes. I hate them so much.
Anyway. Oh, that's funny. No, can you imagine? Imagine for just one moment if the Eagles had won that game, the Giants would have won the division with a 6-10 record.
I know. And Dolphins lost with 7-6.
Yeah. It's happened multiple times where a 10-win team has not made the playoffs.
Yeah. But
it's happened very rarely, I think maybe once or twice, that an 11-win team doesn't make the playoffs. Think about that. It's the way it happens. Anyway, it almost happened this year with the Dolphins. If they had won 11, who knows? Anyway, back to this. Okay.
Like, what was the point of that?
The point of that is that they wanted the number 6 pick instead of the number 9 pick. It had to do with draft picks. Anyway, today is the 4th. Make sure you don't write a 20, write a 21. And this is introducing the concept of inverses. Ooh, that's a good point. I probably should have the chat open. There we go. I'm going to get the chat open on my phone right here, so for those of you that have questions or whatnot, I'd be able to see them. Like I said, I will be posting a PDF to the Google Classroom today at some point. For you guys that are in the classroom with me, I have physical copies of that worksheet. But for those of you that are in the chat, I do have a PDF that I will post eventually. I'm just getting it open on my phone right there. We go. Nice. I can see that there are 6 of you in the live chat right now. Excellent. To this. There we go. So let's talk about what an inverse is. if I had the equation y equals, I don't know, 2x minus 3. Just the equation y equals 2x minus 3. And I'm going to be adding some other stuff to this in a little bit. Let me make sure I got the right one here. I want to make sure that I get the correct equation that I'm going for. Yes. There we go. Second equation, y equals 1/2 x minus 3 over 2. Of course, I could put those as decimals. I opted not to. Decided I did not want to do that. That might be a plus. Let me double check that. Yeah, that's a plus 3 over 2. Let me change that. Easy fix. Bam. Plus 3 over 2. Just want to make sure that I got the correct functions going on here. Now, I call this inverses, and I want to show you why I believe these two functions to be what I define to be as inverses. So what I'm going to do, and I'm going to just ask you to visually see this on my calculator in a moment. There we go. I'm going to zoom in on my calculator. And once it focuses, you'll be able to see those two functions right there. The first function, y equals 2x minus 3. And the second function, y equals 1/2 x plus 3 over 2. Mind you, I put the fractions in parentheses just because it makes me feel better. Look at the graphs. I'm about to graph this thing. Look at the graphs. Chapow, chapeau. These two functions are what I define to be as inverses. There is a reason why they are inverses. There is a reason why visually I define them to be inverses. Now, visually, yes, they cross each other. That doesn't mean anything. There's tons of lines that cross each other. What is so different about these? What is so unique about the visual image of these two graphs crossing each other that makes them to be, in my definition, inverses? Now, again, I have not given you a definition of what is an inverse. All I've said is, hey, they're inverses. Okay, why? How? I'll tell you as time goes on. But what is so unique about this image right here? What is so just kind of nice looking almost? You ever see those videos online where like they like slice something and then like somebody says, this is so satisfying or some junk like that? You ever see those dumb videos? Yeah. There's something strangely fascinating, strangely satisfying about the way that these two graphs look. What is it? Ooh. What is it? I could turn the image like this a little bit. What is it about these two graphs that make them just so strangely satisfying to look at? Well, why? They are perfect reflections of one another. They are reflections of one another. Go back to your geometry definitions. These two lines are reflections of one another. They are reflections over this diagonal that cuts them right down the middle. In fact, I probably do that directly on the calculator. Hold on. Let me put that on the calculator itself, where I could put this third equation in. I'll make it a little bold so you can see it. Boom, there's the third one. If one of these lines were off by a little bit, I bet that would bother a few people. It's like if I leave a mark on the board and people just kind of stare at that mark for a while. They're like, ah. Or if, you ever watch like somebody like coloring in the lines and at the very last second they color out of it? Yeah, it's just like it pains you. But this, everything lines up perfectly. Now, there's something to be said about these two equations. There's something to be said about these two equations. Let's see. Give me a number. Any number. Positive or negative, just make it whole. 5? Okay. Watch this. I'm going to take 5, and I'm going to plug it in to this first equation right here. I'm going to plug a 5 in. And if I plug that 5, where did I get that 5? Well, he told me 5. Okay. If I plug that 5 in for x, what do I get back for y? If I plug in 5 for x, what should I get back? 7. 2 times 5, which is 10, minus 3, which is 7. There's the ordered pair of 5, 7. Yay! Now, let me go back to this graph real quick. Let me go back to this graph real quick on my calculator. Zooming in, zooming in, zooming in. And let me find that ordered pair. There it is, blinking right there. 5, 7. 5, 7. Well, clearly, 5, 7 is not an ordered pair on the other equation. Clearly, it's not an ordered pair on the other equation. But if they are indeed reflections of one another, if they are indeed reflections according to whatever geometric principle that you learned last year, could you guess as to what that ordered pair might be? Think about the concept of reflections. When you look in the mirror, you see your reflection. But what's wrong with your reflection? What's wrong with your reflection? You look in a mirror, what's wrong with it? The opposite. Everything's backwards. Yeah, everything's backwards. When you look in a mirror, have you ever just kind of like thought to yourself, okay, I'm raising my left hand, but it looks like my reflection's raising his right hand? Yeah. It's very strange looking in a mirror and that whole thing, the way that reflections typically work. So again, everything's opposite. Everything's reversed, as you say. If this is 5, 7, what would you expect this ordered pair to be? What's a reflection of 5, 7? What is the mirror image of 5, 7? Yeah, 7, 5. So hold on. Watch this. If you plug in a 7 right here, what's half of 7? What is half of 7? If you say again? 3.5. What's 3.5 plus 1.5? $3.5 plus 1.5. Yeah. There's a very strange thing happening here in terms of what I deem to be an inverse. Inverses have very unique properties in regards to algebra. Functions that are inverses of one another have very unique visual properties and computational properties that we are going to be able to recognize in a little bit. I am telling you that these two equations are indeed inverses of each other. And not only have I showed you visually that they kind of show this weird reflection of one another, but not only that the 5, 7 ordered pair for the first equation, well, there just so happens to be a 7, 5 ordered pair for the second equation. That will happen over and over and over again. Every single ordered pair that you can find in the first equation will have been reversed in the second equation. There's many more definitions that I'm going to get into in regards to inverses. When you hear the word invert, what comes to mind? What do you think about when you hear the word invert? Opposite. Like, give me an example of something in life that you could invert. Like, sometimes it makes sense to invert stuff. You ever put in batteries? plus, minus. If you invert them, don't you put them in wrong? You put them in backwards. You put them in reversed. You put them in opposite. If you invert something, sometimes it can be a good thing in real life, sometimes a bad thing. Here's the easiest example you're ever going to see. If I take 2 steps forward, how do I invert? Take 2 steps back. Literally, that's the easiest example to think about the idea of an inverse. An inverse undoes what you did. It's very strange to think about inverses, but they are important in the concepts of mathematics. Because if you know how to do something forwards, it is vitally important that you know how to do something backwards. If you know how to get from point A to point B, great job. How do you get from point B to point A? Sometimes you can't always go the way you came. Let me give you an example. I grew up in Barnegat. You guys are spoiled in regards to your Parkway entrances. You know that? You can get Parkway North by heading out on Bay Avenue past the Burger King, and you get on Parkway North, right? Cool. You get on Parkway South by going around the Wawa, right? When I was a kid, there was no Parkway South entrance. You couldn't get in Parkway South. You know what we had to do? We had to go Parkway North. We had to loop around Waretown and then go back down south. That's how I know, it's really messed up. How much is a Parkway toll booth right now? When I was a kid, 35 cents. 35 cents each way. It's pretty solid. I don't know. We had these things called Parkway tokens. You ever see them? You can pay like $10. You get a roll of Parkway tokens. It's literally 1 token would count for that. Yeah. Yeah, and they got rid of them. Why'd they get rid of them? They were kind of nice. It's like you get a roll of tokens and take one out. All right. Pretty solid. Anyway, inverses. You undo what you did. So, let me give you a definition, and then we're going to go into a few examples here. First of all, let me just give a couple of notes on this. These 2 functions are inverses for the reasons given in the following definition. I just wanted to specify that these 2 equations, these 2 functions, are what we call inverses of one another for the reasons that I'm about to give in the following definition. So let's say the following. F of x and g of x are inverses if, and I'm going to give you bullet points here because there's a few different definitions. If their graphs reflect over the line y equals x. First definition, f of x and g of x are inverses of one another if their graphs reflect over the line y equals x. Visually, sometimes you can see that very easily. Yeah. Oh, of course. This is why I have concrete notes, because imagine if I erased it. Ugh. Second bullet point. Yep. Every ordered pair, x comma y, every ordered pair x comma y in f of x isn't this standing up right? Oh, because the bottom broke. There we go. Much better. Every ordered pair x comma y in f of x becomes y comma x in g of x. Every single ordered pair that you could find for the first function reverses for the second function. And lastly, and this is based on what we were doing before break, which I'm going to get into. F of g of x, the composition function, f of g of x will simplify to give you an x. If you find one of these properties between two functions, then you automatically can identify them as inverses of one another. Now, what I'm about to do, I'm going to post that PDF that I was referring to into the Google Classroom. For you guys right here, I'm going to pass out that worksheet. So let me get that to you now before I post that PDF. Let's see. Here, PDFs for today. Post. Out. There we go. So for those of you in the Google Classroom, or in the, I should say, the video live stream, in the Google Classroom stream, I posted the PDFs for today. The PDF that I'm looking at, I would like you guys to look at the side 6.2, 6-2. Make sure you're looking at that particular side. 6-2, inverse functions and relations. Now, I'll start off very simply. Look at number 1. And I'll put that on the board in a moment just so we can all see what we're looking at the same thing together. But I'm looking at number 1. Zooming in, zooming in, zooming in. Watch how easy some of this can be. And I say some of this, I mean I'm very specifically some of this. Find the inverse of each relation. Okay. They give me 3 ordered pairs. What do I do? It's like, find the inverse, I guess. Well, I go back to the 3 bullet point definition. The 3 bullet point definition gave me 3 things to think about. It gave me things to think about in terms of graphs. It gave me things to think about in terms of ordered pairs. And it gave me things to think about in terms of composition. They gave me here ordered pairs. Okay, ordered pairs. I could probably let you guess, but watch what happens. Look what I just wrote. I usually do something like that, and I guess what most of you are thinking at the moment. Is that it? Yes, that is it. That is all you have to do for that problem. That is all that you have to recognize for something like number 1. And at this point, you're like, great, give me the test now. I can do this. Well, yes, it's just the first problem, but bear with me. Obviously, for numbers 1 through 6, yes, it is that straightforward. You just simply reverse the ordered pairs. Let's look down at number 7. Number 7 is where it gets a bit more complicated. Now, for something like number 7, they want you to do a couple things. They want you to find the inverse, which I have not shown you how to do that just yet for an equation. And then they want you to graph it. I'm going to do something slightly different. I want you to graph it first. So let's graph this thing together. If you know how to graph things like this, and again, I did not teach you Algebra 1. I do not know who taught you Algebra 1. If I mention anything about Algebra 1, I do not know what type of PTSD you're dealing with. But basically, I'm plotting a y-intercept, which is 0 in this case. I perform the prerequisite rise over run. Rise over run in this case would be up 3 over 4. And I did the same thing down here as well, just to get the other side of that graph. And there's my original function, f of x. Great. Wonderful. How do I determine the inverse? Ooh. This is taking it a little bit farther now. Let me find the right color pen here. Ooh, purple. I might use purple. If I can find a better one. Oh, there we go. Much better. Colored pencils. Come on, you. There we go. I'm going to, purple colored pencil. So I ask, okay, what do I do? What is this ordered pair right here, the one that I'm pointing to? What is that ordered pair? It's 3, 4? Nah. 4, 3. In red, written in red, it's 4, 3. Which means in the inverse, 1, 2, 3, 4. Yeah. That one's got to be 3, 4 in the inverse. What's this ordered pair right here? Which in the inverse would be what? I know that's kind of redundant, but yes, it will be. And then this ordered pair, what is that? -4, -3. Which means in the inverse, it would be -3, -4. I did this in purple to kind of show the contrast between it. But you can see visually, they are reflections of one another. They are reflections of one another. Here's what I want you to do. I want you to take a minute or two, just a minute or two, and I want you to do number 9. I want you to do number 9. I want you to graph number 9. I want you to find those inverted points, and I want you to find the equation of the inverse. The equation of the inverse. Now, the equations here are somewhat straightforward. The original function was 3 over 4x. The inverted function, well, hold on. It's got the same y-intercept. Ah, cool. 4 over 3x. It's never that simple. It's never that simple or that straightforward. I want you to do number 9. Take a couple minutes, knock that one out. Usually if I mention geometry, there's a shiver that goes down most of your spines. Am I right? Several of you are nodding yes. Usually there's not as much PTSD when it comes to Algebra 1. But again, I didn't teach you Algebra 1. So my assumption is that if I give you this equation, you know how to graph it. Y equals 3x minus 2, plotting the y-intercept of -2, and then going up 3 over 1, up 3 over 1. There's my line. Now that's the original function. That's the f of x function. They wanted you to graph the inverse and then find the equation. Now I'm going to show you on paper how to find the inverse in a little bit. But for now, let's just graph the inverse. Well, this is the ordered pair 1, 1, which 1, 1 just stays a 1, 1. This is the ordered pair 2, 1, 2, 3, 4, 2, 4. So it should become 1, 2, 3, 4, 4, 2. See that in purple. This the ordered pair 0, -2. So it should be -2, 0. You can see that reflection already happening. And this the ordered pair -1 and then 1, 2, 3, 4, 5, -5. So it should be -1, -5, -1, -1, 2, 3, 4, 5, -1. There's my purple line right there. What is the equation of my purple line? Anyone find it? Well, how about this? What's the slope of my purple line? Just the slope. Should be 1/3, absolutely. The y-intercept is a little more difficult because it's like, oh God, it's not a whole number. What is the y-intercept? I'm going to show you how to do that on paper. So, if you would, I'm going to return to my notes. Here we go. Here is the equation. Example number 9. Y equals 3x minus 2. How does one find that y-intercept, that correct y-intercept? Well, here's how you do it on paper. This, actually, you know what? No. I'll give you those directions afterwards. Let me show you visually what it looks like. First, write this. What in the heck did I just do? Verbally, somebody tell me, what did I just do? Yeah, that's the whole concept of inverses. You flip x and y. Okay, watch what I'm about to do next. What does it look like I'm trying to do? I did one step. I added 2 to both sides. What do you think I'm trying to do? Say again? Yeah. I'm literally trying to just get y by itself. I'm trying to find what y is. I'm going to divide everything by 3. If I divide everything by 3 here, I'm going to go y equals 1/3 x plus 2/3. That is my inverse. This is the inverse. The steps for doing this are also somewhat straightforward, but you do have to be careful with how you go about them. That is the equation of the inverse. And that matches. That does match what I got here in purple. That does match what I got here in purple. In purple, focus that. Clearly, it's a 1/3 slope, but that y-intercept looks like some kind of a decimal that's between 0 and 1. It looks a little bit closer to 1. Well, based on the work that we just did right here, it is indeed the decimal or the fraction 2/3. So it's how does one go about doing this? Here are my directions. To find the inverse equation. Step 1. There's multiple steps. I'm just going to very carefully walk you through each of them so you know exactly what is expected of you. And then I'll show you how I actually did the first example. To find the inverse function, change f of x to y if needed. Sometimes you will see functions that start out f of x or g of x or some junk like that. Okay, fine. Change it to a y if needed. Now, for the problem that we just did, number 9, it already was y equals. It already was y equals for number 9. So you didn't have to do it. That's why number 1 is if needed. If you don't need to do it because it's already done, then don't do it. Now, step 2. Switch x and y. Literally, just switch the positions of x and y. That is the inverse step. You are inverting the variables. Step 3. Solve for y. This is going to be using some of your solving abilities to do so, of course. But you just solve for y, you get y by itself. And then finally, change y to this. Look what I just wrote there. Look at that strange, ridiculous thing that I just wrote there. What does that look like to you? What number is that? What position does it look like it's in? Yeah, but it's not an exponent. It's actually not an exponent. It's indicating, in this case, the idea of an inverse. It's not saying f of x to the negative 1 power. It's saying f inverse of x. That's what it's really saying. If you look at your worksheet, you'll see an example of this down in number 17. Down in number 17, they show that notation down there. Number 17, part A, find the inverse f negative 1 of x. It's really f inverse of x. So whenever you see that, that's in reference to the inverse. That's what these things do. What was the first example I did here today? Oh, there it is. The first example, and I did this quickly on paper. The first example that I did today was something like this. I decided very quickly in the moment that I was going to do 2x minus 3. And I took a moment and I paused at the beginning, and I very quickly jotted down on paper what the inverse was going to be based on the directions that I just gave. And I just wanted to make sure I got it right. So once I knew I had the inverse, then we proceeded with the problem. Step 1. I'm going to change it to y equals to make myself feel better. Step 2. I'm going to switch x and y, thus creating the idea of the inverse. Step 3. I'm going to solve for y. And in solving for y, I may end up with some of these decimals or fractions, which is okay. But that's what we get. Step 4, I'm going to replace that y with the proper notation to get the inverse. These two functions right here, they are inverses of one another. Step 1, I like to replace it with a y if needed. Step 2, switch the x and y. Step 3, get the y by itself. Step 4, I like to replace it with the inverse notation. They are inverses of one another. They reflect one another. They are mirror images of each other. Every single ordered pair in one has been reversed in the other. That is why they are inverses of each other. It's very strange. Then, I come back to the last bullet point from the definition from earlier. I want to confirm something right here, using these two as an example. F of x equals 2x minus 3. We just did that. Let's just call it g of x equals 1/2 x plus 3 over 2. We just did that. I want to perform the composition. According to the third definition, the third bullet point that I gave you in regards to inverses, according to the third bullet point, what should the composition result in? What should it simplify to become? I'm hearing static. What's the third bullet point say? For inverses. If f of x and g of x are to be inverses of one another, then the third bullet point says that this should equal what? Good thing I have my notes written down. Yeah, it should be x. It should be x. I'm just going to go back to my notes right here. Let's see. Here we go. There's a little paper. That's what I wrote down earlier. F of g of x should equal x. If they are inverses of one another. Now, I'm pretty confident that these two functions are indeed inverses of one another. I'm pretty confident in that. If I don't get x as the result of the composition, then something went wrong. Either I messed up in the equations or I messed up in my computations. I don't know. That's what I would have to eventually figure out. But I'm pretty confident that I'm right. This is what we were doing before break. We were performing composition functions, taking one equation and shoving it inside of another equation, possibly violently, against its... shut up. But I'm going to perform this composition. Let's see what happens. If I take this g of x function, which in this case is 1/2 x plus 3 over 2, I'm going to have to take that function and put it inside of the f of x function. Here is the f of x function. It is the outer shell. It is the outer shell of this problem, f of x. Like a turtle, I'm going to shove the g of x inside of this shell. I'm going to put the 1/2 x plus 3 over 2 right there in that blank. Well, this would become 1/2 x plus 3 over 2. This is the composition function. This is the fifth operation. Now, again, I have not done this composition with you since December 18th. It has been a while. It has been multiple weeks. That is why we need the practice. If I simplify this down, it should become an X, thus proving that they are inverses of one another. If I take that 2 and I distribute it, 2 times 1/2 x becomes, well, 1x, plus 2 times the fraction 3 over 2 just becomes 3, and then minus 3. Lo and behold, I get an X. This, well, for the lack of a better term, verifies inverse functions. That X right there verifies. It proves, it shows, it confirms that the two equations that I had at the top were indeed inverses of one another. Here's what I want you to do. Go back to that worksheet that I gave you. Go back to that worksheet that I gave you. And let's take a look at something like number 10. Let's take a look at something like number 10. And we're going to do this one together. And then I have a couple others that I want you to try. First of all, I'm looking at number 10. There it is. It's focused. Determine whether each pair of functions are inverse functions. And then it says to write yes or no. And we change it out for this one. There we go. Then it says yes or no. Well, okay. Are they inverses? Well, we have multiple ways of going about that. We have multiple ways of going about that. I forgot I had this on here. Let me do this one. There we go. Let me go here real quick. Oh, totally not what I wanted. X minus 6. Oh, it's plus. Nah. X plus 6. And then X minus 6. There we go. Graph. Oh, no. Watch out. Now, there are 3 bullet points that determine whether or not functions are inverses of one another. Number 1, they are reflections of one another across the line y equals x. Number 2, every ordered pair x comma y becomes y comma x in the inverse. Number 3, the composition of the two functions just simplifies to become an x. What do you guys think? Yes or no? Are these two inverses of one another? Ooh. A lot of people immediately stumble on this one. They stumble on this one because these two lines don't cross each other. They don't have to. Go back to geometry. What do you call two lines that don't cross each other? Say again? Parallel. They're parallel lines. Now, just because they're parallel lines, does that mean that they're inverses or not? No. Being parallel has nothing to do with it. Being parallel lines has absolutely nothing to do with being an inverse. Could they be inverses? Yes, they could be. But we need to prove it. We need to prove it. All right. Check this out. Look where I just went. Look where I just went. I just went to the graph. Or the table, second graph I went to. Here's the ordered pair 0, 6 in the first function. If 0, 6 is an ordered pair in the first function, what should be the ordered pair in the second function? Should be 6, 0, which It is. Here is 1 comma 7. What should be the ordered pair in the other function? 7, 1, which it is. Now, does this prove it? Unfortunately, no, it doesn't prove it. It doesn't prove it because guess how many ordered pairs you'd have to check? Guess how many ordered pairs you'd have to check in order to prove it this way? All of them. How many ordered pairs are there? You're not checking all of them. Goodness. So instead, for something like number 10, we go to the following in order to do it correctly. I am going to perform f of g of x in order to prove, in order to confirm, in order to determine, in order to verify that they are inverses of each other. Well, the outer shell is f of x, that is parentheses plus 6. Let me put the g of x inside. Nothing distributes to those parentheses. Oh, look at that. Don't the 6's just cancel each other out? You get x. Yes, they are. If the composition simplifies to just become an x, then yes, you have confirmed it. Oh, happy day. Now, it has to be an x. If it's a negative x, that doesn't count. If it's an x plus 1, it doesn't count. It has to be a solitary x. Let's take a look at number 12. We'll do number 12 together. We'll do number 12 together. And then we'll kind of wrap up with this. Oh, actually, no, I want to wrap up with something slightly different, but we'll get there. G of h of x. I'm performing the composition in order to determine whether or not those two functions are inverses of one another. All right? Here's the outer shell. The outer shell is 13x minus 13. Well, the x is now a blank because something is going to go in that blank. What's being inserted inside is the function h of x, which is a 1 over 13x minus 1. I wrote that in purple so you can see that a little bit better. I got to distribute that 13. If I distribute the 13, it becomes x minus 13 minus 13. Oh, crap. What is negative 13 minus 13? What's negative 13 minus 13? Some people would whisper 0. Some people would whisper negative 26. You need to be careful with what you're doing. For number 12, are they inverses? That's a big O no. Absolutely not. Why? Because you didn't get an x. You got x minus 26. It needs to be precisely an x. Now, how in the heck does this relate to what we've been doing? You just spent the last several months working on polynomial functions. And when I introduced this particular chapter, I specified that we were getting away from quadratics per se, kind of. And we kind of are, but at the same time, kind of not. Look at my calculator. Hey, have you ever been on a graphing calculator and you see those dots in the top right corner? You ever see that? Do you know what it is? No? Some people like panic. I paused the graph. I paused it. Did you know that when you graph, you can actually pause it in the middle of doing it? It's pretty awesome. If I hit enter, it unpauses. Look at that. I'm going to bold this first one. I'll bold that first one, make it look a little bit nicer. This first function right here. Oh, no, sorry. This first function right here, that is the function x squared. I'll put this one in green, see a little bit better here. This function is the function the square root of x, technically plus or minus the square root of x. This is the big crescendo to the whole day. Pay attention to the following couple of questions. Oh, what happens when a square and a square root come into contact with each other? What happens when a square and a square root come into contact with each other? For example, the square root of x squared. What happens? Hold on, don't. I want to know what happens. They cancel each other out. They undo what you did. They invert each other. This is what we're going to be getting into. This is what we're going to be focusing on Wednesday. It's going to be amazing. End class.